How often have we experienced that a small mistake costs us a big impact in the future? Humans are always erroneous. We as humans commit small mistakes which bites us back in the future. A similar arena is cancer detection. Human error and distraction is about 94% of the cancer mislabeling errors. This happens due to mislabeling the samples, where you can see here Brenda and Linda are grouped into different packets. A claim, a recent survey claims that 66% of the lab technicians need improvement in the way they detect cancer. 28% of the patients are misdiagnosed. That's more harmful than a drug or any surgical error. Another fun fact is that MIT and ESA are working on a toilet which could detect cancer. Now, that is a great example of IoT and machine learning. To give you an analogy of what mislabeling can cause, here is a short video.
This is Bob, and this is Alice. They want to diagnose for cancer. They go to a lab where they want to give their samples to a doctor. The doctor collects their blood samples and DNA samples and gives it to Trudy, an assistant. What Trudy does is misplaces the samples and then tries to analyze for their DNA for cancer. Once we have the results, that is presented for the patient. After a few months, we find that Bob dies. Unfortunately, and guess what? Alice also dies. This was because it was mislabeled that Alice has cancer and Bob does not. So therefore, Bob will not take any treatment, and therefore he dies. In case of Alice, she takes treatment, she goes to chemotherapy. Even if she doesn't have cancer, this will cause the good tissues to die, and she will eventually die as well.
This is where we come in. As a part of this course, the final project, we are taking part in the precisionFDA competition, where we are given 3 different data sets, out of which we need to derive a model which can not only detect mislabeling but can also correct the mislabeling by predicting the right values in place of the mislabeled values. Clinical data gives us information about the gender and also their microsatellite instability levels. Proteomics gives us information about their DNA and their background, race, health records, etc. And RNA dataset gives us information about the chromosome pairs, how they react to one another. Data cleaning techniques. So before we even do any machine learning, to analyze those data sets, we need to process them. Taking inspiration from Steve Jobs, who said it's the outliers, it's the misfits, it's the outstanding people who actually can change the world. Same way, we are trying to also enhance the outliers, data which won't fit into any pattern, to check if they give us any result. Now we are writing an algorithm between clinical data and proteomics data, clinical data, RNA data, and combining them to form a model. So we now have data, algorithm, and an insightful result.
We are using the Amazon AWS EC2 instance to access the Jupyter Notebook, and it is also linked with the S3 bucket through an IAM role. So before we get started, let's launch our instance. We are going to go ahead and select the Deep Learning AMI Ubuntu version. It can be 13.0. For our case, as we have a good long amount of data, we're going for m5.large. Next, configure. Selecting the IMI role. So I'm going to go with the EMR EC2 default role. There can also be that we can go for S3 bucket. Next is storage. I think about 50 GB is good enough for our data. I will click review and launch. Now I had created a key pair, so this is my key pair. I will select the existing key pair, launch instances, and I can view my instances. So in here, it's in the pending state. After it's in the running state, I can go into the connect, and I will be able to connect my local system with this instance, EC2 instance. Let me go to my terminal. But before that, let us take a look at our machine learning solution. So our machine learning solution first consists of data collection. We are using the precisionFDA data given to us, after which we are pre-processing the data. This is different from the traditional machine learning techniques. Pre-processing the data also means to remove the bad data. Then we are training our model based on the training set which is given to us. And in the end, we're classifying it whether or not it is mislabeled. Now, the pre-processing the data, we have 4118 features for both proteomics dataset and RNA dataset. So we need to filter out the unimportant datasets and only extract in the most important datasets. After the data has been extracted, or all the important data which is related to our solution has been extracted, we need to cluster them. So we are using the Kmeans clustering, and as you can see here, it is divided into 4 different clusters. The same process is repeated for RNA, and it is clearly seen here that there are 4 good clusters created. There are always some data which do not fall into any clusters, and those data are obviously dropped. As it is in the running state, let us go into connect and let us follow the steps. Now I need to open my terminal. I'm going to type in, I'm going to SSH into the EC2 instance. This command is generally used if you want to make our SSH work publicly seen. Let me SSH it. Say yes. So now my local system is connected with the Amazon EC2 instance. Now in order to access my Jupyter Notebook, I just need to type Jupyter Notebook. Now I need to take this URL and type it into my search engine, and it will open a Jupyter Notebook where I can write my code. So I have done that, and here is my code which I had written, which is the train RNA. First, I need to import the important libraries like NumPy, Pandas, and Matplotlib. After which, I need to load the sumtab2 CSV data file, and then the train RNA CSV. Now here is the data. Taking a transpose because I want the training to go here. And here is how it looks. Now I have NaN values which are not applicable. So first we decided to replace it with 0, but then even a 0 has its importance. So we decided to replace it with the mean of each row for every individual row. Now, from my sumtab2, I have taken the RNA sequence data into the Y. So this is how it looks. sklearn ensemble, let us import the random forest classifier, and then we have kept the max step to 10, which means that we want our decision tree to be up to 10. After which we are extracting, after that we are putting our fit, we're doing the model.fit on our data. So X was the RNA training data and Y was the RNA clinical data. On that we are doing a model fit, after which we are extracting the 10 most important features after the random forest classifier has been performed. So here is the feature importance of the top 10 features, from which we are just taking 2 most important features which we think contributed more towards our output, and we labeled it as X reduced. Now, on that X reduced, we are performing a K-means clustering. So, by performing a K-means clustering, we will have 4 clusters where each of these features will fall into one of these 4 clusters. And here, it is clearly seen that there are 4 different clusters which are formed. Now, we are putting each and every cluster data into one of the 4 arrays, which is A, B, C, or D. Now, we are refining this data more by removing the MSI high and only contributing the MSI low. We're doing the same thing for A, B, C, and D, and hence we're calling it as A refined, B refined, C refined, and D refined. Appending the 4, we are getting to know that there are 62 correctly labeled samples, while 18 are mislabeled. Let us follow the same procedure for test RNA dataset which is given to us. So importing the important libraries, loading our data, replacing the NaN values with the mean, then performing random forest classification to deduce 10 most important features. After which, we're performing K-means clustering. And on performing the K-means clustering, we can see that we have 4 unique clusters which are being formed. And all those features, or from the reduced features that which was in the pre-processing phase, has been divided or has been fit into 4 different clusters. Now we have also done the linear SVC to see if our data does actually cluster itself, and we found out that the score was 98%. Then we take 4 different arrays and divide our clusters into one of these arrays, and then we remove the MSI high from each and every array to get a refined. Now in here, as we see that after appending A refined, B refined, C refined, and D refined, we get about 66 correctly labeled samples.
So going through the algorithm, the first step is replacing the NaN values with the mean values. When we go through the dataset, there are few values which are not given to us, and those are mentioned by NaN. We need to replace those values by a certain value. We tried replacing it with a 0, but we got better results when we replaced it with the mean value. In order to do that, we will go through the code. First step is importing the important libraries and loading the data file. After loading the data file, we will check the data file. So right now we are using test proteomics, and as we can see over here, there are few NaN values in all the testing samples, and we will replace those with the mean values. In order to replace them with mean values, we will apply x dot mean on every row and replace it. Now as we can check over here, the NaN values are now replaced with the mean values in all of them. After replacing it with mean, next step is using random forest classifier. The reason why we are using random forest is because it takes Gini as the criterion while giving the importance of every feature. Now Gini index is maximum when the distribution is normal. The distribution is normal when it is most scattered, meaning it will take all the outliers into consideration while giving us the importance of every feature. Now, as we wanted to do it differently from the traditional machine learning methodology, we are using random forest along with the Gini index while giving us the important features. The important features are required for removing the data which is irrelevant or less important. So first step is importing random forest classifier from sklearn library. After importing random forest classifier, we will fit the model on the dataset and the target, which is provided in sumtab2.csv. After that, we will plot the top 10 important features. As we can see over here, these are the top 10 features which are the most importance while keeping Gini index into consideration, and while keeping the Gini index as maximum. We will put them into COLS and get X reduced, which will have just few of the features from 4118 features. Once we get the reduced dataset, we are going to apply K-means clustering. For that, the first step is importing Kmeans from sklearn library, and we are going to create 4 different clusters based on the MSI label. The MSI label are MSI high, low, based on male and female, and we are going to fit the X reduced on Kmeans. As we can see, the first sample belongs to cluster number 1, the third sample to cluster number 3, and so on for rest of the 80 samples. In order to see how sparsely they are distributed and in which cluster to the samples belong, we will be using plt.scatter. As we can see, 4 different clusters are found which are clearly distinguishable, and each of them represent MSI high, low. So for example, the samples in green might be MSI low and samples in yellow might be MSI high. In order to check that, we will be comparing it with the clinical data, which has the MSI label. So for doing that, we will be creating 4 different arrays, and we will append all those samples in 0 cluster to A, all the samples in 1 to B, all the samples in 2 in C, and similarly for those belonging to cluster 3 in D. As we can see, almost all of the samples in cluster A have MSI low, so we will assign that cluster MSI low label and drop those which is MSI high, as that is the next step in the algorithm. We will implement the same method for B, C, and D. Again, MSI low is dominant over here. For C, MSI low is again dominant, and similar results are found for MSI in D. On obtaining all the results, we will add them up to check how many are labeled as correct and how many are mislabeled. As we can see, 66 out of 80 are labeled as correct, which means 82.5% of the samples are labeled correctly, while 17.5 are labeled as wrong. After dropping the odds, we will check the dropped ones for duplication swap. So just to be sure how sparsely the clusters are divided, we will be using SVM, support vector classification. So from sklearn, we will import SVM and apply linear SVC for classification and check the score. We are getting a score of 98, which means 98% is the amount of differentiable clusters. So after dropping the odds, we have to check them and put them in the right place. So as we can check over here, training 65 sample and training 72 sample are clearly swapped. So the next steps would be putting them into the right place, which have been swapped and which have been duplicated. Those have to be correctly sampled again. So all of this was done on test proteomics data. We have also done the same for training proteomics. We will quickly go through the whole as the method is exactly the same. The clusters which are found are different, and those which are labeled as wrong are different. So we'll quickly go through the code, importing the important libraries and the data set, after which we will replace the NaN values with the mean values. and import random forest from sklearn for feature importance. These are the top 10 features based on the Gini index. Take XReduced, implement Kmeans by importing it from sklearn, plot how the clusters are formed. So there are 4 different clusters and they are distinguishably separable. Then put them into 4 different arrays in order to check which MSI label each of these have. So in cluster A, which is cluster 0, majority are MSI low. For cluster B, majority are MSI low again, so we will drop those which are MSI high. For cluster C, majority are MSI high, so we will drop MSI low. And for D, low is dominant, so we will drop high. 64 is the total number of samples which are labeled correctly, which means 16 out of 80 are labeled as wrong, which is 20%. So 80% of the samples are correctly labeled. So this was what we did with proteomics data. We applied the same for RNA data as we saw before, and all of this was done on Amazon EC2, after which we launched the Jupyter Notebook.
We now realize that cancer is an expensive disease. A small misdiagnosed treatment can cost you around 30,000 US dollars. And in case you lose an organ because of a misdiagnosed tumor, that'll also cost you around $15,000 for lawsuits. Not to mention, it affects the mental health of the family as well. All this can be avoided by taking a second opinion, like we always do, but this time it's with a machine which runs on cloud. We are using AWS, Amazon Web Services, to run all the algorithms, which cost less than $100 to be, and so that the patients can be extra sure about it. Not to mention that the algorithm always keeps getting better. Here are some of the references. Thank you.